so what values can AB have? Well, it's not one of those 5, all right? And AB... Yeah, similar to here. Now AB, we can get, so we've got rid of 5, so let's get rid of another one. And AB cannot be equal to BA squared. Why is that? Well, let's prove that that's the case. Well, let's assume that it is true, and we'll get a contradiction. So let's assume that AB is equal to BA squared. And now A squared is B squared, right? So you get here B squared, there it is, B squared. So, therefore AB squared, in other words, you put a B here and here, so AB squared will be this with another B here, so it will be B squared B. So that's B to the 4th, but we just showed here that the order of B is 4. So B to the 4th here is just E, right? Now, where'd this come from? Where did this come from? Damn, I'm forgetting myself. So why is A equal B to minus 2? Where did that come from? Oh, from here. Okay, so AB squared is E, right? AB squared is E. So therefore A equals B to the minus 2. Okay? But the order of B is 4. So B to the minus 2 is just B to the 2. Okay? So therefore B squared is A. So B squared is A. Not A squared. If that's true, if AB equals BA squared, you deduce B squared is A. But B squared is A squared. And A squared are different elements, right? They're different elements in your group, right? These two here, A and A squared, are not the same element, right? They're distinct elements. And therefore we have a contradiction, okay? So AB cannot equal BA squared, all right? So we've eliminated a 6th possible value. So we're left with just 2 cases. Either AB is BA, as before, or AB is BA cubed. Right? So now we have 2 subcases again. Alright, so let's do case 2.1. So we'll take this case. So AB is BA again, so your group is abelian. Now comes a trick, and I had to scratch my head. I was looking in Barnard, in the text, and I was asking myself, where the hell did that come from? Why did you do that? So you're now benefiting from my thinking. I'm writing between the lines of what's in the text. Okay, so this is a trick. It works. That's why it's done. Take the product of A and B inverse and just call it C. And you may ask, well, why the hell do you do that? Well, it works. Right? You'll see the consequence that it works. So let's just do that. So okay, so C equals AB inverse. Now B, we showed down here, has order 4. So B inverse is just B3, B to the 3rd. Okay? So C squared will be AB cubed squared. Right? So just plug that in here. So this is C. So that comes out as A squared B to the 6th. But A squared is B squared. Oh, wait a minute. A squared is B squared. Yeah, that's case 2. A squared is B squared. Right? We're in case 2, 2.1. So A squared is B squared. So this B to the 6th is the same as A to the 6th. Right? So this becomes A to the 8th. But A to the 4th is E, because the order of A is 4. Okay, so A to the 8th is E, so you just get E. So C squared is E. Right? So the order of element C is 2. Right? And that implies the inverse of C will be 2 to the power 2 minus 1, which is just C. So when you have an element that has order 2, its inverse is itself. Right? Done that quite a few times. So the inverse of C is just itself. Right? Okay, so what can we deduce from that? Well, by definition, C is just A B inverse. Right? Now, post multiply on both sides B and B. So you get CB equals A, B inverse B, which is just A. Right? So you get CB as A. And now let's solve for B. So left multiplies both sides, C inverse, so you just get B equals C inverse A. Right? But C inverse A is just C. We just did that just a moment ago. Right? So B is equal to CA. Right? So we can now rewrite these 4 elements in the following form. We just showed that B is CA, so B becomes CA. So BA will become CAA, which is CA squared, and BA squared will be CA times A squared, that's CA cubed, and BA cubed will be CAA cubed, which is CA to the 4th, and A to the 4th is E, so that's just C. Right? So we've rewritten, by this trick, by doing this trick, we have rewritten these in the following form. Right? So instead of having B, BA, BA squared, we can write them in the following form. Okay, so that's your group written in terms of C rather than B. And by writing it in that form, we get a group table. Now it's a bit of a trick, and it's not obvious, but when you use these elements using the value of C, you will get a group table that's isomorphic to this one. Right? So we've done that before. So for this case, for case 2.1, we just get again C4 by C2. Right? So we do not get a new type of non-isomorphic group. We've just got this one again. And the point behind doing this C trick was just to get the group table so that visually you see that it's isomorphic. Right? So this is not a new case. All right, now let's do the last subcase of a case. So the fourth. So this will be case 2.2. And let's see, what do we have? So we know A to the 4th is E. A squared equals B squared. That's from here, case 2. And the subcase, we had 2 possibilities, right? So AB is BA, that was this one that we've just done, or AB is BA cubed, the second subcase. So AB is BA cubed. Now, if now for A and B, they're your generators. They're rather abstract, but if you give those abstract elements of your group a concrete form in the form of 2 by 2 invertible matrices of this form. So if you let your A be this matrix, right, and you let your B be this matrix, then if you find A and A squared and A cubed, using this matrix, you'll find that these elements here, B and BA, BA squared, BA cubed, and so on, where B is this, you will find that this is a group. It's actually a group. You can prove that. Now, and in fact, it's a subgroup of the group of all possible invertible 2 by 2 matrices. Now, why say that? Well, when you're trying to prove something's a subgroup, if you prove that it's a subgroup, sorry, to prove that a subset is a subgroup, if it's a subset of a group, then you inherit the associativity from the parent group. Now, in general, matrices are, so long as they're well formed, matrices are associative. So matrix ABC, A brackets BC, is the same as brackets AB C. So matrices are associative. So this, if you could show that this is a subgroup of the general group of all possible 2 by 2 invertible matrices, therefore you don't have to in proving that this is a group, a subgroup, you don't have to prove associativity, because you've already got that from your parent group. So you only have to do the other 3 tests. Well, you've got an inverse, you've got closure, now you can see that from the group table. Now you've got 8 elements, so you'll have 64 entries in your group table. When you construct the group table, you'll see that you get closure, right? Any entry in your group table will be one of these, so you have closure. And from